Have you ever really wondered how a computer actually learns? It can feel like magic, but it's not. It's actually a lot more like a detective story. Because when you get right down to it, learning is all about one simple idea: assigning blame. And today, we're going to crack the case of how an AI figures out it made a mistake and traces it all the way back to the source.
So let's set the scene. You show a neural network a picture of a cat, and it says, with total confidence, "Yep, that's a dog." Okay, so it's wrong, but that's not the interesting part. The real mystery is, what happens next? How does it actually learn from that blunder so it doesn't make the same mistake again? That's what we're digging into.
And to get our heads around it, we're going to use an analogy. Think of this whole process as a detective story. And our main clue, our guide, is a simple relay race. Seriously, this analogy is the key to understanding everything.
All right, first things first. Before we can solve the crime, we have to witness it. This is the part of the story where our team of runners actually runs the race. We're about to see the final outcome, which is where our crime, the wrong prediction, actually happens. A neural network is basically just a relay race team. The input layer, all the pixels in that cat photo, that's our first runner, grabbing the baton and taking off. The hidden layers in the middle, those are the middle runners, each one taking the baton, running their part of the race, and passing it on. And the output layer, well, that's the anchor runner, the last one in line who makes the final guess as they cross that finish line.
Now, in the world of AI, this whole sequence has a fancy name, a forward pass. But don't let that fool you. All it means is the race is run from start to finish. The information, our baton, only moves in one direction, from the start, through the middle, to the end. Simple as that.
And here are the results from the race. Our network finished with a score of 0.855, which, in its world, means it's pretty darn sure it's looking at a dog. But the truth, the actual correct answer was 1.0, which stood for cat. So yeah, our network was confident, but it was confidently wrong.
And this number right here, this is everything. This is the total error. It's the gap between what our network guessed and what the truth was. You can think of it as the exact amount of time our relay team lost the race by. This single number is the problem we need to solve.
So how do we fix it? Well, a good coach doesn't just storm in and yell at the entire team, right? No way. A good coach investigates. They figure out exactly what went wrong and where. And to do that, you have to start at the finish line and walk the track backward.
Okay, now the technical process for this uses calculus. And I know that word can be a little intimidating, but for our detective story, just forget all the complicated formulas. Think of calculus as a tool. It's the math that lets our detective go up to every single runner and ask one simple question. Exactly how much did you affect our final time? That's it. That's all it's doing.
So the investigation starts with the last person who touched the baton, our anchor runner, the output neuron. It looks back at the runner who handed the baton to them and basically says, look, our final time was way off. And you, hidden neuron number 2, you gave me a really, really strong signal. That means you had a huge impact on my guess. So right now, you're my number 1 suspect.
And this brings us to a key piece of evidence, the gradient. It sounds complex, but a gradient is just a number. It's the precise calculated amount of blame that gets assigned to each and every connection for its role in that final mistake. It's like an official blame score. Now here's the cool part. The blame doesn't just stop with one runner. It gets passed backward down the line. The anchor runner blames the middle runner, who then turns around and blames the runner before them. In mathematics, this whole process of passing the blame backward, link by link, is called the chain rule.
So imagine that middle runner, now feeling the heat. They turn around and say, whoa, don't look at me. I only ran that fast because the connection from input pixel number 45 was super bright. It gave me a strong push. So yeah, if you're blaming me, you have to blame that connection too. And just like that, the blame keeps flowing backward.
Okay, the investigation is officially over. Our detective has interviewed every single runner, every single connection, and has assigned a precise amount of blame, that gradient, to each one. Now the coach steps in. It's time to use all that information to actually fix the team and win the next race. In this coaching session, believe it or not, also has a name. It's called gradient descent. This is the process where the coach goes to every single connection and makes a tiny, specific adjustment based on exactly how much blame it got. We're not firing anyone from the team, we're just making little nudges to make the whole system better.
So what does this coaching actually look like? Well, it's all about tweaking these numbers, these weights. You can see here the connections that got blamed for the mistake get nudged just a tiny, tiny bit.
It's a sum of all these microscopic adjustments across the entire network that, together, we call learning. And here is the absolute key to the whole thing. The direction of that nudge is crucial. If a connection was blamed for pushing the final answer in the wrong direction, the coach nudges its weight in the opposite direction. You're basically telling it, hey, you pushed a little too hard that way, so next time, ease up a bit. That's how it corrects the error for the next attempt.
So why did we walk through all this? Because let's be real, you're probably never going to do this math by hand, but understanding the logic behind it is what's truly important. Your job isn't to be the calculator, it's to be the coach.
The great news is, modern software does all of this heavy lifting for you automatically. It's called AutoGrad. But understanding this backward flow of blame is like having a superpower when you're trying to figure out why a model isn't working. It helps you diagnose problems, like the famous vanishing gradient, which is basically when the blame signal gets too quiet to reach the early runners. By understanding this, you now get the core logic of how machines really learn.
And that's really the big takeaway here. Don't get bogged down by the calculus. The core idea, the logic, is incredibly simple and intuitive. You make a guess, you measure how wrong you were, and then you walk backward, assigning a little bit of blame to everyone who contributed to the mistake so you can make tiny fixes for next time. That's it. That is learning.
Which kind of leaves us with one last big question. If a machine can methodically trace, quantify, and correct its own mistakes, doing it over and over thousands of times a second, is what it's doing really that different from what we call learning? Something to think about. Thanks for tuning in.